So Gyuszi is graduated from 1987 from the University in Romania. I don't know how to say that name, but where's Gyuszi at? How do you even say this? Cluj-Napoca. Okay, great. With a degree in computer science and engineering, he's been at Intel since 1993, where he has worked on several generations of design wheel modules and synthesis tools, spanning nodes measured in microns down to a few nanometers, a few being 7 to 10, you know. Gyuszi is the main architect of and co-author of Boost Polygon, which was contributed to SI2, which is called OAX Pop. It's a very popular Polygon operators. Gyuszi has 4 patents related to physical design. His passions include drawing, math, puzzles. He even brought a puzzle today for us. C++, he's an early developer of C++, and he now teaches that. He's the main organizer of Intel's annual programming contest. His name is Hungarian and it's pronounced similar to juicy, as in juicy fruit, okay? I'll introduce Gyuszi, and then when the panel starts, I'll introduce Jason Kane, the panel moderator.
Hello, I'm Gyuszi. Thanks for having me here today. Let me see if this works. Forward and back. All right, cool. I brought a puzzle with me. This is a wood. I made it out of wood. This one describes the. I was using this as a prop to show my colleagues the basic idea of the language. We called it fruit. Actually, my colleagues called it juicy fruit. I didn't name the language, but they said it's a good pun. I worked on design rules for many years, like a quarter century, and this is, I think, the 5th generation that I worked on, and it was getting better and better over time, and I think this time around I said that I think it's good enough to take it to open source. And so the basic idea is that you have multiple objects relating to each other, right? So you can have coordinate systems, gridding, because what I've seen that over time, the rules became more and more complex in terms of the geometrical relationships that they had and the number of objects that were playing into the rules, right? So at the beginning, we just had simple end-to-end rules. Then the end-to-end rules became intervals or Bezier curves or ovals or circles with knockouts and whatnot. So the geometry was getting more complex, and then over time, more objects came in, 2 vias, 3 vias, 5 vias, 11 vias, cuts, plugs, all kinds of stuff, and then it became really, really complicated to comprehend the rules and to write tools that can actually create layout that is compliant with those rules. I also wrote a reference manual. It's fresh off the press. I printed it on so it's only 1 copy. I will hand it around if you want to just kind of flip through the pages. All right. I'm going to go to my formal presentation. So that's why I put the fruit there, because the internal language is called fruit. All right, so that's the agenda. I'm going to talk about what is declarative language and what are patterns and matching and why now. And I will give you a few examples of rules written in this language. I will show you some matching layout. I will talk about the vision. I will give you a status of the code and the data model and work to be done, and I will invite for collaboration. All right, so I'm using a few examples of rules here, and none of them are Intel IP. I just came up with them, and I'm using also a few rules from OpenDFM, so I'm not giving away any Intel IP. So what is declarative language for geometric pattern matching? So formal language, formal means is so that computers can understand it. That's the short description. And you can see it's a language designed to use in situations in which natural language is unsuitable. I've seen thousands of rules in my life. And about 500 of those thousands I couldn't understand. And I had to go to the person who wrote the rule and say, what did you mean when you wrote this thing? And if I give you a Boolean language, ands and ors, well, how would you change your sentence? I say, oh, shit, I didn't write this language, the sentence properly. I said, yes, you did not write the sentence properly, so why don't you put it in some mathematical terms? So when you corner them in a situation, they always hit their forehead that, I screwed it up. So it became more and more obvious that we need to have some kind of formal means of communication. As declarative versus imperative, which I will give you a foil on what the difference is and why this is really, really meaningful. And capable of describing geometric constraints of any complexity between any number of layout objects that are gridded or gridless or any combination thereof. Now, I designed the language to be able to describe any rule of any complexity. Does it do it today? Probably not. I mean, you can probably come up with like a fractal-shaped rule with 55 million objects that the language cannot describe, that requires recursion and whatnot. I think the infrastructure of the language is designed so it can scale, it can grow, we can add more geometric functions to it. So once I show you a few rules, the natural reaction is to challenge me, and my colleagues challenged me, and the panelists challenged me with rules. So your natural instincts will be, hey, can you do this rule that looks like a, I don't know, helicopter with some guys dangling from it? And maybe I will be able to describe that rule. But I think more importantly, we can discuss how can we make the language such that it will be able to describe those complicated rules. And gridding and gridless, what it means, I don't know if I'm using the same term as you guys are familiar with, but what I've seen is that the layout objects, shapes and sizes are becoming more discrete. We used to live in a world where every shape, every dimension worked with polygons and any distances, and now I see that things are being chopped. Sometimes you have to express rules for gridding, sometimes for not. So I made a mistake in the past that I did the language only for analog, then only for discrete, and Fruit does both of them, or Opal. It's a Freudian slip if I call Fruit. I'm supposed to call it Opal. All right. So let's look at regular expressions. So I wrote a regular expression there, which is it's supposed to find some characters in a string. So let's say the A pluribus unum is a string, and it will find these three matches. Similarly in layout, let's say I have that layout that looks like the T and I and an inverted L. I want to be able to describe some pattern that looks like the inverted L, maybe mirror, maybe not, and I call it pattern P. And similarly, as I do it with regular expressions, I should be able to find these things. Now, is this a good pattern or bad pattern? That is not really relevant. It's a pattern of interest, right? Most traditionally we find bad patterns, and if you have no bad patterns, then the layout is good. But you could go the other way around. You could say, I only find good patterns, or not whatever, right? So the regular expression doesn't say that that regular expression is good or bad. It's something of interest. LUR or BUS is something of interest. So I think the main questions are, how do we define a pattern? How do we match the pattern in the database of strings or layouts? And then how to create a pattern-compliant, clean layout. I will not talk about number 3. I will leave it up to you to figure that out. I have some ideas. I have some history on how I have done it. But today we're going to talk mostly about how to define the pattern. Is the language that we provide good enough? Is it easy to understand, easy to write? And then I will talk a little bit about how to match the pattern. Now, if you're interested more, you can look into the reference manual, and I have a whole chapter on matching and binding. Okay, so why now? The process rules are getting more complex with every generation. You know that. Everybody knows that. And I also see that the process nodes live longer. They used to live for periods of time, and they die, and the new process node comes along. And now we have older process nodes from kilometers down to nanometers. So it's like a lot of rules, and they keep changing, and they keep adding dot processes to it. So the number of process stacks we have to deal with is growing. And gone are the days when we have pairwise object rules, like via to via, wire to wire, wire to wire. And advanced rules involve multiple layout objects in complicated relationships. And there's a lot of inefficiency, at least one I see. Maybe it's not universal, but what I see is that there's a lot of inefficiency. And also there's a genuine interest from SI2. And Jake is here. He showed a lot of interest and draw. So I felt this love coming from Jake. So I said, why not? So let's say we have a chessboard, and we have the now infamous 193 nanometer wavelength to print the chess pieces. And let's say in layout, that would show up as maybe a via to via rule. So on the chessboard, it would be maybe 2 pawns have some relationships, some relationship between each other. And on the layout, we have 2 vias that can or cannot be at a diagonal location. Well, the chessboard shrinks every 2 years, but the wavelength stays the same length, right? So now the same wavelength may affect 3, 4, 5 chess pieces. And in layout, it may show up as like a complicated relationship between multiple vias or plugs or wires or diffusions or poly or TCN or whatever, right? So even if you go to EUV, the problem persists, because things are shrinking, so you're always going to have more and more objects that you have to deal with. So let's say we have this rule that this black pawn can capture this white pawn, unless the white pawn is in a trio of 3 collinear white pawns. And then the collinearity clause can be overruled if the total number of black and white pawns in this rectangle is odd. How would you define that rule? Now, it's a made-up rule, obviously, but the complexity is realistic. I have rules that are more complicated than these that I have to deal with. Okay, so that takes me to the declarative versus imperative. So on the left-hand side, there's a trick on how to do a swap between 2 integers without the temporary objects. How many of you know this trick? Raise your hand, please. About 2, 3. So I will walk through it. So you have A and B are 2 integers. These are C language. And I want to swap them. So if I do A equals A XOR B, that's a bitwise XOR. And B equals B XOR A. And A equals A XOR B. You swap the 2 variables without the need for a temporary. And there's a state diagram showing it goes from state 0, where A is value 7 and B is 15, all the way to when they are swapped. So it's a sequence of calls, of commands, of imperative commands, that at the end result is that you end up with what you wanted. You end up with a swapped state. Now you can achieve the same thing with temporary, where you have A, B, and T. T is a temporary, and you say T equals A, and A equals B, and then B equals T. And you have a different state diagram there, where 4 states, where A and T and B have different values. At the end, you end up with the swapped A and B, and the variable T is at value 7. These are both imperative implementations. You achieve the same goal by different means. So imperative is a series of commands or orders. A sequence of states tells you how to do it. Now, in contrast, a swap A comma B would be a declarative. You're declaring that A and B has to be swapped. You're not saying how to do it, you're saying what to do. Right? So declarative declares what needs to be done, what the expectation is, tells what to do, not how to do it. And then there is path to go from declarative to imperative, to either of the two. Those green arrows show the paths. It's possible. You can also convert it to German, Tausche, A and B. That means the same thing. However, going from the imperative to declarative is not possible, or very, very difficult. So imagine that imperative code is 1,000,000 lines of code that does all kinds of things, and at the end you end up with a painting of Mona Lisa, right? How do you reverse engineer that the meaning was you wanted a Mona Lisa painting? It's not possible, right? And the reason I'm bringing this up is that the tools that have to synthesize layout, they need to have a declarative model. They need to have a mathematical model of the rules so you know what you build. And the run sets typically, irrespective of who wrote them or what vendor we used, dating back in the early 90s, we always had imperative run sets. And taking that stack, which is the sign-off tool, and figuring out what it meant so that the routers, placers, fillers, and whatnot, cell synthesizers know what to do is very difficult. So that was a manual process. So today's landscape is lithography and process realities in a yellow box. And there's humans, many people who try to convert that reality into in English and drawings. And then there's a bunch of other people who convert that English and drawings into a sign-off checker, which is imperative. And then we have a bunch of tools, internal, external, doesn't matter what it is, the problem is universal. And then we need human conversion from the orange box and the red box into the gray box. Why do we need to have an arrow from orange to gray? Is because the sign-off checker is imperative and it's hard to understand. So people go to the text, which is not complete, the drawing, which is not complete, the checker, which is complete but imperative, and trying to reverse engineer a declarative model for the tools. And then we have another tool, and if you have 50 tools, then you have like 100 yellow, 100 blue faces there, all converting this stuff. So the process is lots of manual steps, it's time-consuming, it's error-prone, incomplete, imprecise, and dumbed down. There's one more thing. There's once you have a language, then people start to express stuff that they were not able to express before. So if you give people only PowerPoint, they only can do so many drawings. If you give them something more expressive, they start, oh, now I can express this. So the means of communication improves by languages. And there's theories on that, on how it affects, the language actually affects the brain functioning. All right, so in this, how many minutes do I have?
You have till noon.
Oh, I have till noon, okay. I will introduce a few rules, and the rules are only rectangle based, so I will not have polygons in these rules. And I have a few properties on the rectangles, like x low and x high and x center and the delta on the vertical, delta on the horizontal. So stuff like that. Okay, so this is, how many of you have participated in the webinars I gave in January or December? So only a subset of you. So let me do a detailed walkthrough. So this is the first time for most of you, first time that you see Opal code. So Fruit was the original internal name, so sorry for that, but it's now called Opal. So a rule end-to-end simple, that's the name. Excuse me, I thought I have a laser pointer. That's okay. Do I have a laser pointer on this? Maybe not. That's okay. So the first line says rule name end-to-end simple. Then we have a constant, minimum end-to-end is 100. Nanometers, kilometers, doesn't matter what it is. Then we have a Boolean end. And then we have the first line, which is a wire yc equals 0. That means, so what the green wire is some kind of layout object type. Let's say it's metal 1 wire or metal 2 wire, something that is known to the designer. And A is just an identifier. YC equals 0 is a relative number. And the next line, B wire YC equals 0. So we have an A and B, two objects, and all we know that their Y center is 0, and this is relative. So it's not 0 on the layout, it's 0 relative to each other. So they are lined up on the Y center. And there's that so after the B line, there's a vertical bar, that's the such that, it's a guard expression. Distance A to this on horizontal is less than minimum end-to-end. So this is the green is the type of the object. Could be metal 2, metal 1, whatever you want, from a set of known types. And then the A and B are identifiers. Those are optional identifier names if you need. Then you have, so that yellow line represents the objects on the left. That orange line represents the object on the right. And there's a guard expression in oval. and that means the distance between A and this. So this is refers to B, where that's the object that's being defined at that line. On the horizontal dimension is less than minimum end to end. Okay, so that's the guard expression such that B's distance to A on H is less than minimum end to end. The vertical bar is a guard expression, also known as such that. Okay. Do I take questions here or not? You want me to move on or?
Move on, I guess.
Move on, okay.
But if there's something that somebody really has to ask, go
Yes.
ahead.
If you really are puzzled by this, let me know. If not, then we can talk. I can talk to you for 24 hours on rules if you want. You just give me water and a sandwich and I'll go till tomorrow. I don't know if you want that though. Okay. So now we're going to a little bit more. So it's, okay, one more thing. So here, I say that the two objects are lined up on center. Now, sometimes we have end-to-end rules when they are misaligned slightly, right? Then the rule should be changed slightly that the y-center is not the same, but they are within an interval, or their projections on the y-axis are touching or intersecting or containing or whatever, right? So if that's the rule, you would have to add an extra clause there.
Gyuszi,
Yes?
does this say that the distance between A and B should be less than the minimum?
Okay, good question. So remember, we are looking for a pattern. I'm looking for a pattern where the distance is less than 100. Somebody else has to say whether this is good or bad. Now you could put it a good category or a bad category, it doesn't matter, but we are capturing it, right? Same like a pluribus unum. I caught the U and U. Is that good or bad? Well, I wrote a pattern, and if I found it.
What is the output of the rule?
Well, the output of the rule, let me delay that. I have a foil on that. Okay, so let's go to the next page. So now we have the same end-to-end distance rule, except that the guard expression that's on the second line, or the last line of the rule, works on an interval set. So if you see those red arrows at the bottom here, these ones and the green one, those represent areas of interest, intervals of interest. So if the distance between A and B is in the red interval, then the pattern is matched. If it's in the green interval, the pattern is not matched. Right? So now let's look at that line in, and there's a curly brace, and the curly brace says 0 to end V1, that's open, that's an interval, comma, a second interval, and you can see the line at the bottom with red and green and red, and I put DRV, so now what Matt asked, I say, if it's red, it's a design rule violation. Now, there's a dot here, a green dot, which means that the edge of the B comes here and touches it, that would be okay. If the edge of B is in the red interval is not okay, the green is okay, red is not okay, all the way to here, and okay beyond that. Right? So we can play with these numbers as needed. All right. Let's go to a more yes. Top button is laser. Oh, yes. Thank you. All right, so let's have a more sexy rule. This is an airplane rule, and I have the English description on the left, and I'm going to walk you through it. So it's a jet plane that's not supposed to have a propeller. So the first line says a fuselage has to be between 33 to 44 or 55 to 66 feet long. Then on the so in the code I say fuselage, F fuselage. So the fuselage green word is a type of layout object. Let's say metal 2. I call it F. F is the identifier. Fuselage is the metal 2, which we know goes horizontally, maybe. And then you have the bar, which is the guard expression, which means such that F dot delta on H, which means the length of the fuselage in the x dimension, is in interval set 33 to 44, comma 55 to 66. And that line means there exists a fuselage such that its length is such and such. Okay? Now the next line is the wing of 46 feet or between 49 and 52. So we have wing, the name is W, the type is wing, let's say metal 1, so it has a certain width. such that delta in vertical is in a different interval set, which spans from 46 to 49 to 52. So the first line says there exists a fuselage such that. The second line says there exists a wing such that. Now, with a cockpit on the left end contained by the fuselage. So imagine a cockpit is a VR1, right? So you have a C cockpit such that contains F comma this, which means the fuselage contains the cockpit. So this line. The fuselage F contains the cockpit, this. And this dot XH is less than WXL. So that means the XH of the cockpit, which is the right edge of the red, is less than the left edge of the orange. So we guarantee that the red is left of the orange. And with a tail on the other right end somewhere. So here, with a tail on the other right, say there's a tail here. So this dot XL, which is the tail, that's the left side, is larger than width of XH. So now we know that the tail is right of the orange. The wing should encompass the tail in the y dimension. So we have to take the projection, the vertical projection of the wing and the vertical projection of the tail and make sure that the orange contains the green. So that means contains wing to the tail on the vertical dimension. The wing and tail should cross the fuselage. So I have this clause that the fuselage intersects the wing and the fuselage intersects the tail. This is the tail that we are talking about. And the plane should not have a propeller. So this line says we have a propeller called P such that it intersects F and this. I could have said contains, so it wasn't clear. Oh, excuse me, intersects the propeller, right? And not of that, which means does not exist a propeller such that the propeller touches the fuselage. All right. So let's say we have layout, and the layout, we have six kind of airplane-looking thingies. And if you apply this rule, it will match 3 of those. This one is an airplane. This one is an airplane flipped to the right. And this one is also an airplane. It doesn't look like an airplane, but according to what you wrote in the rule, it is an airplane. If you don't like it, then you should have lined up the centers of the wings with the center of the fuselage or given some other clauses, but based on the clauses written on the previous page, this is an airplane. And this is not a jet because it has a propeller. So I'm going to move to an SI2 OpenDFM rule. So this is a real rule. I will explain, this is from the OpenDFM manual. That's the description. And this is my drawing. I will explain you what I understood from that rule, and then I wrote the code for this rule the way I understood it. So if we have a mid-wire, I draw 2 Mickey Mouse ears, one on the left, one on the right. This Mickey Mouse ear has a certain dimension called Parse space and EOL within, relative to upper left corner of this rectangle, and there's a symmetric one on the right. So there's 2 left ear and the right ear. If we have a left neighbor whose upper right corner or bottom right corner is in the blue box, and we have a right neighbor whose upper left corner or bottom left corner is in the blue box, then if we have a top neighbor that's perpendicular to this one, there's a spacing constraint, the attacker rule spacing constraint. Okay, so the code is so I have some constants here, some values, EOL within, EOL space, and Parse space. Of course, you could use these numbers directly here, but sometimes it's more easier to read if you have some constant name associated with a constant. If you just put an 80 there and another 80, maybe they mean 2 different things. And then when you have to change the rule later on, you have to go and find all the 80s. So it's better to go with symbols. You don't have to. So the first line here in the meat of the rule, we said we have a wire called mid, and the x low is at 0, yh is at 0. So I put the reference coordinate, the 0, 0 of the coordinate system at the upper left corner. I just chose it so. It's all relative, right? So the mid wires 0, 0 is here. Then we have a top wire, and this is from x low to x high. So this is x low and this is x high. So the x low of top, okay, so this is 0, 0. And the left side of top can be from infinity all the way to this blue line. And the right side of the top can be from this blue line to the infinity, right? That's what this means. So the x low is from infinity to 0, and the xh from mid xh, which is this side, to infinity. And the bottom of the top, the y low, is between 0 and UL space. Now, if it touches, it's not an attacker rule anymore. It makes a T. So that's why this is 0 open parenthesis. If it would be square bracket, it would be, touching would be also part of the pattern. It's not part of the pattern, so it's between 0 and UL space. If it's already at UL space, then the rule doesn't apply anymore. So that's why you have open parenthesis to open parenthesis. Okay? And then we have the left wire and the right wire. So the left wire has to adhere to some constraints, and the right wire has to adhere to some constraints. Let's look at the left wire. So the left wire exists such that the distance from left to mid on H is less than Parse space. So the distance here between this wall and this wall is less than Parse space. And the corners, there's some absolute value, there's an OR between them that puts one of the corners in the blue box. And then we have a similar one on the right side. Same stuff, distance and then a corner. And if you look at these two codes, they're pretty much similar, right? So that's it's an opportunity for writing a function. So on the next page, we define a local function called corner in blue boxes. So this code is the same. This function says, is A in the blue boxes? Is a corner of A in any of the blue boxes? And then we have a left guy and the right guy. So let me read the rule now. I have a mid wire. I have a top wire that has some constraints on the here. And I have a left wire such that its corners are, any of its corners are in the blue box. And I have a right wire such that its corners are in the blue box. And then corner in the blue box is defined here. Okay. So I'm going to talk about grids. So here I define a grid. Let's call it M1 grid. The period is 100. That's the that arrow is incorrect. This arrow should point to the 100. So the period is 100, offset is 0, and the pitches are 0, 25, 100, 125, 150. So you go like boom, 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 chaka, boom, 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 chaka, boom, 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 chaka. That's the rhythm of your, if any of you is a drummer, you can relate to that. And it's vertical orientation. And then I have a metal 2 grid with a different period of 60, and the offset is 0, and the pitch is at 0, 20. So it goes 0, 20, pause, 60, 80, pause, 120, 160, pause, and so on. And then we make it horizontal here, like that. So we say orientation is horizontal. Now you can read the values here on the right. All right. So now this is my last rule. And then I'm going to talk about some logistics. But this is the last example of a rule. And it looks like a lot, but it actually expresses a lot. So bear with me. We have two grids defined. So M1 grid and M2 grid defined as on the previous page. So we have offset, period, and pitches. Then we have the name of the rule, and then we have some constants. Okay? Basically, I'm looking for an object A, and I create a donut around it of radius d1 and d2. And I want to count all the vias in the donut of a given type that are gridded. And I also need to have some other random wire poking in with its bottom right corner, also in the d2 radius circle. Then I have a match. So A via 1. So via 1 is a type. That's all the blue rectangles are via 1, such that X center is an M1 grid. So M1 grid are the vertical lines. So the center of A has to be on a black line, and the Y center has to be on an orange line. So notice that this center is on intersection of black and orange. Okay, then we create a set here, and the set starts here and ends here. So this is the definition of a set. This is with the let notation. Let neighbors in the donut, this is a stupid name I picked, neighbors in the donut equals set of types via1 and via1 big. Via1 is blue, and green is via1 big. Such that, so now we say what is the condition of membership in the set. These three lines describe that. A dot C, which is the center of A, Euclidean distance to this dot C. This is the element that will be part of the set. So the center of A, Euclidean distance to the set element center, is in the D1, D2 interval, square brackets. So it's, this is, touch is considered. And so these three conditions are ended. This dot XC is on M1 grid. So the center of these guys, the candidates, are on the X1 grid, on M1 grid, and the center Y is on M2 grid. So this guy will get me 1, 2, 3 objects on the set. This object is on the set, this and this. This is not on the set because it's not on the center. This is centered on the X but not on the Y. And this is on grid but outside of the radius D2. So only 1, 2, 3 objects will be on the set. And then this one says the count of neighbors in the donut is larger than or equal than LL, and the count of neighbors in the donut less than or equal HH. I could have used one line here and put this in square bracket LL to HH. Okay, so we are looking for conditions for 2 to 4 neighbors in the donut. The last line here is that we have a wire called M1 wire called B, such that the distance of the A dot center to this dot edge on south and edge on east, which will give me the southeast corner. We actually have a better function for this one, less than D2. And that the bottom right southeast corner has a distance constraint to A center. Now, I've seen rules like this, and they are like, one full page of English and drawings, and it's not complete. And they have to go back and say, did you mean less than or equal? What happens if they're aligned? What happens if it's on top of each other? And conditions, and nothing replaces math, right? No matter how hard they try, there's always going to be some unspoken truth and cause for confusion. So the vision for Opal is that there's only one manual step in the whole process. When somebody knows what they're doing, they're defining the rule in Opal. These would be the lithography guys or the process guys or yield guys, whatever. And they write what they mean in Opal. And then all the subsequent steps would be automatic. So test layouts can be generated from Opal. Run sets can be generated from Opal. Online checker can be generated from Opal. The drawings and text can be generated from Opal. Internal models for tools can be generated from Opal. All automatic. So all those green arrows would be automatic. I have proof of the online checker. So this is working. It's actually uploaded to SI2 website. I have proof for this. I have a tiny proof for this. It's also uploaded to the SI2 website. It's not a complete solution by far, but it proves that you could do it if you wanted to. And I'm getting an intern next week who will work over the summer on this arrow. And hopefully by September I can report back that this arrow is also covered. So what we uploaded to the SI2 website, we have the grammar in BNF, we have the parser, we have the abstract syntax tree, which is the data model, we have the online checker, which is the pattern matching, we have a language reference manual that I handed it out to you guys, test cases with example rules, and sample seed algorithm for converting to polygon-based run set. This is based on the boost polygon. So here's this is how, when you parse the rule, what happens is that this is the rule, let's say simple rule, A, B, C are wire, such that A contains B, and there's some or between Manhattan distances between A and B and A and C. So when you parse this code, And that's how the rule is, let's say, notice here there's a Euclidean distance relationship between A and C, corner to corner, or either way. And then there's a Manhattan distance relationship between C and B. And A has to contain B. Then the data model shows up like this. There's a lot of boxes. You don't have to necessarily know all the things, but this AND node shows up in the tree as an AND somewhere here. And this is all parsable and checkable in the data model. And then the A exists, right? So this means that exists a wire called A. It shows up somewhere in the data model. And this OR node shows up as somewhere else in the tree. And the Manhattan distance shows up as a function. And these are, so all of these become lambda functions that are interweaved into the data model. Actually, they're all smart. So all the nodes on data model are smart. As soon as the data structure is built in memory, the pattern checking engine is ready. So the rule text equals data model equals checker. There's no extra work. You write the rule, you have a checker. You have a data model and checker. Now the checker is online checker, and this is not meant to replace run sets because I don't know what it scales in speed, but it's formally equivalent and does for small tests, it does a very good job. So for example, so that's that. And then what's not done yet, we don't, yes?
What does an online checker mean?
Online checker means that you have, let's say you have these layouts, and it will say, I match this rule, or I match this pattern and this pattern, this pattern. It finds, just like the regular expression, you write the regular expression, finds the instances in the text. The online checker finds instances in the layout that match your pattern. Did I answer your question?
That's understandable. Why do we call this online?
For a lack of a better word. We can talk in the recess. So I don't have it yet, but hopefully by September we'll have it ready that you will get a set of patterns that match your rule and a set of patterns that don't match your rule, so that the rule writer can visualize, is this what I meant or not? If this is not what they meant, they better upgrade the rule a little bit. This can explode, of course. If you have 15 objects in a rule, it can blow up to billions of combinations. So we'll have to do some filtering. And then we don't have mirror matches. So the vision is that you would define the rule only once. Let's say you define this guy, and then it would match all the other mirrorings accordingly. If you want them. If you don't want it, you will say, I don't want mirroring on X, I don't want mirroring on Y. But normally, things do mirror. And obviously, I don't want to expect the rule writer to write it 4 ways. It would be stupid. We don't have that. We don't have native polygon support. We are planning on adding that. I have my good friend here, James, and the winner of the programming contest of 2016, which is a big deal, out of many, many top programmers. And he is a master of, just as his last name says, Jim, he's a master of polygons. So hopefully he'll help me put in the polygons in the Opal. And we have some plans on having some advanced grid coordinate system, absolute coordinates, relative coordinates, modular coordinates, and that's not added to the language yet. I can talk to you about if you're interested. And we don't have SWIG interface to scripting. The code is written in C++ 11, so it's not trivial to SWIG it. So I will need help there. And we released the code recently, a week ago. It's fresh off the press. It took me about 2 months to clear the Intel legal hurdles, 100 steps. I wrote a chronicle of 100 steps I had to go through to clear the legal hurdles. And it uses Flex and Bison and Boost Polygon and C++. Now, the Boost Polygon could be replaced with OAX POP, so that's an option, and the C++ standard library. And the data model, abstract syntax uses template metaprogramming and lambdas. And then we have to fill in the location of the code and make files and that kind of stuff. The last foil I have is I'm welcoming feedback, welcoming code contribution development, obviously. We'll be willing to teach and mentor the language to anybody. We're willing to work closely with SI2, and I think we will all benefit if we collaborate. And I want to thank Jake and John and everybody in SI2 to set this up for me. And that's all I had.